Okay, so you want to calculate the angular momentum of this ball and the linear momentum. So what I do is before I even read the question is I go through and I pull all the information I can out of the question first, and I convert it to SI units. That way our calculations will be accurate. For example, in the first sentence it says a ball that weighs 17 newtons is attached to the end of a 39 point centimeter long string. 17 newtons is, we can tell from the unit on the end, it's already a standard unit. It is a force. So I'm going to represent that with a force. Force equals 17 newtons. Okay. We don't have to do any conversion there. We just know that the weight, force of the ball, we converted weight to force, if you will. It's more of a translation than a conversion. But the units themselves didn't have to change. Now the 39.5 centimeters, on the other hand, since that's representing a length, I'm going to use little l. We need to actually convert that into a standard scientific measurement, such as meters. And we do that by dividing 39.5 by 100, or you can just slide that decimal over to the left 2 units. You can just slide this over 2 units, and that's what I'm going to do. That's the same thing as dividing by 100. The result there is 0.395 meters. This is the correct unit that we want to be in. What other information does it give us? The ball swings in a horizontal circle so that the string makes an angle with 26.2 degrees with the vertical. The figure did not show up into Wyzant, so I'm just going to draw what I assume this looks like. Um, I don't know if it's above the x-axis or below the x-axis. For this sake, for the argument's sake, we're just going to say it is below the x-axis, okay? So it's doing a horizontal circle, which just means that it is, it just means it's like moving in a horizontal circle. I'm going to do my best to draw it, but it's moving like this in a nice flat circle that's more long. Oh, look, it corrected me. Cool. And it might be moving to the left, it might be moving to the right. It really doesn't matter which direction it's moving. But what it is important is the angle that it makes with the vertical axis. And it says it's making a 26-degree angle, 26.2 degrees. I'm going to write that up here with our units. I'm going to say that the theta with the vertical is going to equal 26.2 degrees. Okay, that's also important to use, to know. Now this like rotation can be happening below, it could be happening above, but it really doesn't matter where it's happening because the calculation and the process will still be the same. So let's continue onward with the question. If the ball travels with a speed of 7.22 meters per second, meters per second is a velocity, that's a unit of velocity. So I'm going to use V for velocity, 7.22 meters per second. What is the angular momentum of the ball about the axis of rotation? Axis of rotation being the vertical y-axis in this case, the horizontal axis of rotation is the x, which is the direction the ball is traveling in, but it's rotating about the y-axis. And I assume it's kind of like this. Like I said, it could be inverted. It doesn't matter because the calculation will still be the same regardless if it's down here or up there. So it's looking for angular momentum. Angular momentum is always represented by a big capital L, and it's described as a relationship between your linear momentum, P, times some radius, R. Neither of these terms were provided to us. So in the question, P or R, we got to find both of them. And it doesn't matter which one we find first. So let's find P, the linear momentum. Let's find that one first. And it's going to be kind of a ride. We're going to go on the ride here. So get ready. P is going to be equal to what? It's your mass times velocity. So that's nice because we know what velocity is. We have one of these equations. We have velocity, but we don't have what the mass is. But we were given a clue to what the mass is, and that is this 17 newtons here. The mass is not 17 newtons, but the downward force or the weight is 17 newtons. Recall that force given by Newton's second law is just the mass times acceleration. Because it's a weight, that acceleration is in the downward direction, and that's acceleration is going to be given by gravity, right? So really we want to use this one. Force equals m times gravity, where gravity is just what? 9.1, 9.81 meters per second squared. All right, so this is what we're going to kind of use to find what the mass is because we're dealing with weight. So if we took this 17 newtons and plugged it into our mg equation here, we got that equal m times gravity, but gravity in this case is 9.81, right, meters per second. So to find the mass, you just need to divide by 9.81, divide this by 9.81, and that should be very close to 1.7, if I recall, if I can do my mental math right. Oh, but I'll just use my phone to calculate it real quick. 17 divided by 9.8, 9.81. And yeah, it's like 1.73. So let's use that. 1.73 kilograms. So this is the mass of the ball. Good. So we can come back to our linear momentum equation and plug that in. So I'm going to do that right underneath here. Should I say organized? Over here. So P equals mass times velocity, and the mass we just calculated to be 1.73 kilograms. Velocity was provided to us. That's 7.22 meters per second. Very good. So this approximately becomes, I don't know, like 12 or something. Let's run it through the calculator real fast. 1.73 times 7.22. Yeah, 12.4. 12 point, is it 4 or 5? We'll say 5. I got 4.9, so I'm just going to use 7.5, 12.5. Okay. And that will be kilograms times meters per second. Good. This is the linear momentum P right here. This is what we're going to use going forward. So if you go back to your angular momentum, we have half of it. We have the P value. We don't have the R value. We did all that work just to find half of this equation, and that was the P value. But now we need to do a little bit more math to find what the R value is. Now, what that R value represents is not the length of the string, but it's how far the ball is rotating here. So the ball's at the end. How far is this from the axis of rotation, the radius here? Like how far is that distance? That's what we need to calculate. We know that the length of the string was 0.395 meters, but we don't know the distance from the ball to the center of the axis of rotation. But as you can see here on the screen, is we have a little right triangle. This ball traces out a little right triangle here, which means we can use trigonometry to find this length of the radius on the bottom here. And if you recall, I don't know, SOHCAHTOA or whatever, this is the opposite side. The side we're trying to calculate is the opposite side. It's opposite over hypotenuse equals sine theta. and we know what our theta is. Our theta was given to us as 26.2 degrees. The hypotenuse was also given to us. It's just the length of the string here, this 0.395 meters. So using a little bit of math, you get O equals, I'm going to move the H up over here, sine theta, and then I'm going to plug in the values. So, and I'm going to replace, remember this O is just R, this H is actually the length of the string, and then sine theta is just sine theta. So this is what it looks like in physics terms. This is from your, the OH sign is from your trigonometry class. The RL sign is from your physics class. So I'm actually going to use this one. And that's going to be R equals the length of the string, which is 0.395 meters times sine of our given angle, which was 26.2. Now this we definitely need a calculator for. We can't just run this through our head. At least I can't. So let's see if we can't get that in there. So I'm going to do approximate. What is the sine of 26.2? I hope my calculator is in degrees here. I think it is. Let me see. Yes, okay, that's in degrees. And I'm going to multiply that times 0.395. And so I found the radius to be approximately 0.17 meters. And we just have to ask ourselves, does that number make sense? Does this radius make sense with that? Well, the length of the string was 0.395 meters, and that's a pretty long string. The leg of the triangle needs to be shorter than 0.395. Basically, R needs to be less than the length of this triangle. So it is. So that actually is a good approximation. That's how we know we're kind of on the right track. Okay. So that's what R is. R is equal to 0.17 meters. And so once we've deduced what R is, we can now take our R and our momentum that we found, and we can plug them into our linear momentum equation to find the total linear or angular momentum. My bad. L stands for angular momentum. So we got 12.5 kilograms times meters over seconds. Multiply that towards 0.17 meters. Run that through the calculator real quick, and well, let's see what we get. 0.17 times 12.5. That's about, no, it was 2.125. Please use like a scientific or graphing calculator when doing this. I'm using my phone calculator, and it's really, really complicated. But the units are going to be kilograms and then meters squared per second. That is the total angular momentum. If you're looking for the magnitude of the angular momentum, is that what it says? It says magnitude up there. Then you just take the absolute value of this. Basically, you take the absolute value, which is just going to turn it positive. So it's the same thing. The magnitude is also, you just take the magnitude of your angular momentum, but all that does is just turn your answer positive. So if we had a negative number, it would be become positive. Okay, so I hope that helps you understand the problem a little better. And if not, I'm sure there'll be other people who come along and also answer the question and maybe offer a different approach. But yeah, thank you for visiting my presentation.